Okay, so let's start off with a simple question. What actually are esters, right? So esters are compounds with a distinct aroma that are derived from a reaction between carboxylic acids and alcohols. So esters can be found in nature, for example, in fruit and flowers. Esters are responsible for the fruity and sweet smell we notice when we smell fresh fruit. A use of these natural esters is in like goods that have aroma. For example, perfume. You want to use perfume to smell good. That's what you actually smell when you smell perfume is the ester itself. Esters can also be synthesized to form compounds that we use in everyday life. An example of non-natural esters are like medication. So as you can see here, I've put a medicine that was actually used to treat COVID. So if someone was sick with COVID, you would give them this medication, and that would hopefully make them feel better. Some other examples would be, let me think, artificial food flavoring, solvents, and plastic. So those are some of the basic examples. And over here, I have provided the basic structure of an ester. So basically, what this means, if you don't know how to read these, it means that you'll have a carbon here, or no, that's the only carbon. So um, as you can see, this radical one, that can mean that any other groups could be in there, and you have radical two, another group could be in there. As you can see, you might notice that this carbonyl, kind of looks similar to what a carboxylic acid would look like, right? And that's actually because this part here, this carbonyl, actually is derived from the carboxylic acid. Okay, so let's start with the actual reaction. So there are different methods of forming esters. All of these methods include a reaction between a carboxylic acid and an alcohol. These are like the two compounds that are needed to make any ester, so any ester you'll ever find is made from these compounds. How are esters actually formed? So there are different methods of making esters, but all methods they have to include a carboxylic acid and an alcohol. These are like the two compounds that are needed to make any ester. So whether you find your ester in medicine or in nature, it was formed with a carboxylic acid and an alcohol. So the reaction that I'm going to teach you today is called a Fischer esterification. It's the most common esterification, and it occurs when you have an acid catalyst, which increases the rate of an ester production, and it smells nice. Okay, so now let's actually move on to the actual mechanism. So say you have your let's say you have acetic acid or ethanoic acid, and we'll take an isopropyl alcohol. Okay, so or this would be like two propanthol. Okay, so let's just write that and ethanoic acid. So let's start by drawing the lone pairs on the oxygens because lone pairs makes everything easier in life. And there we go. So let's start with the mechanism. So first thing you'll notice is that what we can do is let's look at the resonance structure of this. Let me just write hydrochloric acid because we'll use that. That's the acid catalyst. So let's look at the resonance structure. Well, what can happen is this lone pair of electron, or this one on this hydroxyl group, can actually attack this carbonyl carbon, and we'll send this lone pair back, or this bond. And what we'll get is we'll have this resonance structure. So we'll have this positive oxygen with this negative oxygen. So when we add hydrochloric acid, we'll have a partially positive hydrogen, partially negative chlorine. So since this hydrogen is partially positive, it's going to want to protonate this oxygen, this carbonyl oxygen, not this hydroxyl oxygen, because opposites attract. So now if we go back to our original resonance structure, just makes things a lot more easy if you look at it like this. What can happen is this lone pair can form a bond between this hydrogen, this partially positive hydrogen. Hydrogen will send its bond back to the chlorine, and what we will get is this intermediate. We'll have a positive oxygen carbonyl and this chlorine. Okay, so next thing that happens in the reaction is, since this oxygen is positive and oxygen's like really electronegative and it also has this proton attached to it, or this hydrogen now, this carbon here, this carbonyl carbon, is going to become partially positive because electron density is moving away from it to the oxygen. So what will happen is we take our propantool, it will actually want to react with this partially positive carbon. So what will happen is a lone pair will get like donated there, and since this pi bond is the weakest bond here, it will get sent back to this oxygen. This one here. So what will happen is we will get this intermediate. This will form a tetrahedral intermediate. The electrons from this pi bond get sent back to the oxygen, and this oxygen will become positive, and just like that. Okay, so now the problem here is that to form our ester, we need to get rid of this, first of all, this proton and this hydroxide group. Okay, and also this one here, this proton here. So what will we do is we'll take another one of these propantools, and what will happen is this will become like an electron, I like to call it like a proton, shuttle. So what it will do is it'll take this proton and send the electrons back to oxygen, and then we will get this thing here, this intermediate, this one here. Yeah. So plus we'll have an oxygen bonded to two hydrogen in the propantool. So now that this proton has been, put on this shuttle here, I like to call it, what will happen is this pair of electrons here, they can donate a pair to get this this hydrogen, send it back, send those pair that will bond back to oxygen, and what we'll get is we will have. So now, what do you think will be the product of this reaction? Well, let's see, we'll have this, this hydroxyl, sorry, attached to this OH2, connected to this oxygen, connected to this, So what can happen is a lone pair from this oxygen contribute to like a pi bond, which will cause this, like this group here, to leave as water. So that will leave as water, right? And we will get, by itself, we will get a, we'll have a, like this intermediate. So now, let's see. Well, we want this oxygen to have, first of all, we want it to be neutral, and we want to get rid of this proton for it to be an ester. So we can actually just bring along one more of these isopropyl alcohols or propantools to attack the hydrogen, send this bond back to oxygen, and then we'll get one of our products, which is the ester actually. We'll get this product here, and we will get the this product here. Okay, so right now we want to regain our catalyst. So what we can actually do is we can just add that the chloride we got from earlier from the breakdown of hydrochloric acid. You send the lone pair there, send that back, and then once again we get, first of all, we get another propanol, but then we get our hydrochloric acid back. So these are the three main products we get from the reaction, along with the water. There we go. All right. So let's write that down here in our original reaction. We get this plus our water, because the hydrochloric acid was just a catalyst. And yeah, so now let's get to naming this ester. So now when we name it, what we'll do is we will actually just draw a line down the middle. So that's what I'll do. I'll draw a line down this oxygen. So we'll split it into two parts. First, we have the alcohol part, and we have the carboxylic acid part. So what we will do is first, we always start the name with the alcohol part. So this alcohol, this is going to be isopropyl, right? And here, this carboxylic acid, we know we used, this is obviously like ethanoic acid, right? So what we'll do is we have to remove this oic acid. And what we do is we start the name with the alcohol part. So we put isopropyl, and then we have ethanoic acid. We remove the ethanoic, we get ethan, and then we add OH for esters. So this is the IUPAC name of the compound we just created. Yeah, so that's basically it. Or you could call it isopropyl acetate, but I just like calling it, ethanoate, because that's more scientific. You can actually visualize the ethan, but acetate is just as good. So I guess that's all. Thank you for watching the video. It's kind of bad, but hope it teaches you at least a bit. Thanks.